Okay, in this tutorial we're going to do some examples of computing the kinetic energy for different systems. Okay, so for example, the easiest might be if we have a mass, m, and it's moving along a ground plane like this at some velocity. Now, we need to invent a coordinate system. So, for example, the coordinate system might be in this direction. So this might be maybe x, y, and z. And so the position to there would be, let's label that as x. So the velocity vector of this mass then would be equal to, so this is a velocity vector, let's just put the arrow to remind ourselves, would be x dot 0, 0, because there's no velocity component in the y direction or the z direction. So the kinetic energy, if you remember the formula, kinetic energy is going to be 1/2 mass times the velocity of the center of mass transpose velocity of the center of mass plus 1/2 omega, that's the angular velocity vector, transpose j omega. So in this particular case we don't have any angular velocity since the mass is not rotating in any way, and so this would be equal to 0. And so the total kinetic energy then is going to be 1/2 m times the velocity vector x dot 0, 0 transpose times x dot 0, 0, which is equal to 1/2 mass x dot squared. So the total kinetic energy is given by this formula, which should be familiar from high school physics. Okay, so let's do another example. So example number 2. So in this case, suppose we have mass 1 and mass 2, and they're sliding on a surface, again in a planar direction. And now let's suppose that the first mass is attached by a spring and a damper, and that these two masses are attached together by another spring and a damper. Then what is the kinetic energy of this total system? Now the kinetic energy is not affected by masses and springs that are connected to the system. So again, it comes back to, since there's no rotation about center of masses of either of these, I guess we can consider these as point masses, the kinetic energy is going to be 1/2 mass times mass 1, velocity 1, transpose velocity 1, plus 1/2 mass 2, velocity 2, transpose velocity 2. So again, we need to have a coordinate system. So if we have the x direction, y, z, then the velocity of the first mass is going to be, so I guess we need a position. So this position would be x1, and then from the same point out here would be x2. The velocity of the first mass would be x1 dot 0, 0, and the velocity of the second mass would be x2 dot 0, 0. So the total kinetic energy then is going to be 1/2 mass 1. V1 transpose V1 is just going to be x1 dot squared plus 1/2 m2 x2 dot squared. So this is the total kinetic energy of this system of particles. Okay, now let's do a slightly more complicated example. So this would be example number 3. Again, we'll do something that's moving in the plane. So in this particular case, we will, let's have a mass of mass M connected by a rod of length L, but the rod will be massless. A massless rod. Okay, and then for the next example, maybe we'll have a rod that has mass. So again, because the point is a point mass, there's no rotation about that point mass. I guess there's several ways to do this, but we'll look at simply the velocity vector of the point mass. So again, the kinetic energy is going to be equal to 1/2 mass times the velocity vector transpose times the velocity vector. So the question is, what is the velocity vector? Now we can parameterize this system by specifying that the angle from hanging straight down is theta, and we also need a coordinate system. So we could attach a coordinate system maybe to this point. So that would be x, y, and z. So the easiest way to compute the velocity is to first compute the position. So the position vector here is going to be equal to, so in the z direction, we'll assume it's in a plane. And then in the x direction, this distance here is going to be L sine theta. And then in the y direction, this distance is going to be, because y points up, it'll be negative L cosine theta. The velocity vector then is the derivative of the position vector, p dot, and the only thing that's moving here is going to be theta. So L is assumed to be a rigid length, and so when we take the derivative of p, we get L sine theta. When we take the derivative of, let's say sine, we're going to get L cosine theta, and 0. So this implies that V transpose V is going to be L squared sine squared theta plus L squared cosine squared, theta. This will be, when we take the derivative, we'll have L sine theta. The derivative is with respect to time, so that there should be a theta dot on each of these things. So we'll have theta dot squared, L squared sine squared theta plus theta dot squared. And of course, dot is always used to mean time derivative. So p dot is defined as dp dt. Same thing, theta dot is equal to d theta dt. And when we take the derivative of a vector like this, we're taking the derivative of each component. So V transpose V, we can pull out a theta dot squared and an L squared, and we're left with sine squared theta plus cosine squared theta, which is equal to 1. So this is theta dot squared L squared. So the total kinetic energy, K, which was equal to 1/2 mass velocity transpose velocity, it's going to be 1/2 mass theta dot squared times L squared. So that is the kinetic energy of this particular system. Now, as one final example, let's do the same problem, only assuming that the mass has, or the rod has mass. So we have a rod that's hanging down, and now this rod has mass, let's say mr, and then at the end is another mass. We'll just call that m1, and again, this is the angle theta. Okay, so now in this particular case, we have two objects with mass, and so the kinetic energy, and one of those objects, namely the rod, is going to be rotating about the center of mass. So the kinetic energy in this particular case is going to be 1/2 m1 v1 transpose v1. So that's the kinetic energy of the mass without the or the point mass, just like we did before. And now we're going to have the translational velocity, or kinetic energy due to the translational motion of the rod. So this would be mass of the rod, velocity of the rod, transpose velocity of the rod. Plus, we're going to have the rotational, or the kinetic energy due to the translational motion of the rod, 1/2, and then in this case we have omega of the rod, the inertia of the rod, times omega r. Okay, so with the translational velocity, everything is pretty much just like we did before. The velocity of the first particle is going to be, so if we remember from before, we computed v transpose v to be theta dot squared times the length squared. So if we go back here, we're going to have, I guess we don't need to, let's see, I can figure out how to erase. Okay, okay, my erase button is not working. So this part right here is going to be 1/2 m1 theta dot squared times L squared. And now because the center of mass of the rod is at length L/2, you see, then the kinetic energy for this part is going to be plus 1/2 m2 or mr theta dot squared, and then we're going to have L/2 quantity squared. And then we still have this last term, 1/2 omega r transpose jr omega r. So we need to go figure out how we compute that term. So the first thing to point out is that the so this system is going to rotate about the center of mass, and the rotation is all going to be in the z direction. So again, this is x, y, it'll all be in the z direction. So the angular velocity then, and what is the angular velocity? So it's actually going to be, so the rotation about the center of mass is just the derivative of the angle theta dot. So omega, and it's all going to be in the z direction. So omega r as a vector, there's not going to be any rotational component in the x or y direction. It'll all be in the z direction, and it's theta dot. So if you have a term that looks like this, I'm sorry, that should be a plus. You have a term that looks like that, omega r transpose j omega r, and omega r is 0, 0 theta dot transpose, and then we have this matrix, let's just call it jx, jxy, jxz, jyx, jy, jyz, jzx, jzy, jz times 0, 0 theta dot. When we multiply all of that out, because of the zeros will cancel with everything, we're going to get theta dot squared times jz. And so for planar motion, we're only interested in the inertia about the z-axis. Now, this is the inertia about the center of mass, and so that's an inherent property for a physical system. So let's lay this rod out, I guess, in a way that makes it easy to compute jz. So the rod is of length L, and the center of mass is right here in the middle of the rod. And so let's call this the x, or I guess in this case it'll be, the x direction. So the inertia matrix I guess to be able to do this problem, we need to go back and talk about this inertia matrix a little bit more. So let me actually sidestep over here, and let's talk about J for a minute. So we came up with a formula in the lecture where we talked about the kinetic energy for J, and that formula looks something like this. We integrated over the body, and then we had R transpose R times identity minus R transpose. These are all vectors. Times dm at the position R. Now, if we have our body B, and again at the center of mass, we're going to attach a coordinate system, x, y, z. Then this vector r, I guess, will be the value along the x direction, the value along the y direction, the value along the z direction. So R transpose R identity minus R, R transpose is equal to x, y, z, x, y, y, z, times the identity matrix, 1, minus x, y, z times x, y, z. Okay, and that's going to be equal to, so we'll have the identity matrix, each element from here is going to be x squared plus y squared plus z squared, and that will appear on the diagonal, x squared plus y, 0, 0, x squared plus y squared plus z squared. And then we're going to minus this matrix, which is going to be x squared, and then x, y, x, z, y, x, y squared, y, z, zx, zy, z squared. And so that's going to be equal to, because the x squared cancels out on the first component, y squared plus z squared, negative xy, negative xz, negative yx, and then x squared plus z squared, minus yz, minus zx, minus zy, x squared plus y squared. So if we go back and look at our formula for j, remember j, we have that large component times dm. So j then is going to be equal to the integral over, all, I guess, x, y, z in the body of this matrix dm, if it's the same, I guess, of uniform density, then we integrate over position, and dm is equal in every point. So we're going to take that matrix and plug it in here. Okay, so now we want to go back to our problem, and notice in this particular case that we're only looking for the z component, so we can actually write jz is equal to the integral, and now we're integrating just along this rod. So we're going to integrate actually along the extra, and so y will be 0, so we'll just have x squared dm, and then we're going to integrate along the rod, so we're going to integrate from minus L over 2 to L over 2. And let's see, let me zoom back in here. And dm, we're just going to assume, that this rod, I guess, the mass dm at x, because this dm is actually going to be at x, so we'll assume that if that size is just dx, then the mass that's here is going to be the total mass of the system times dx. So jz then, jz, we can pull the m outside, minus L over 2 to L over 2 of x squared dx. And of course that is going to be mass x cubed over 3, evaluated from L over 2, or minus L over 2 to L over 2. And that's equal to mass times L cubed over 24, minus L cubed over 24. And so the inertia is mass L cubed divided by 12. So that's jz. All right, so Now we need to come back to our example. Okay, at this point we have this last term. So let's see, the kinetic energy here then is equal to, K is going to be equal to, from the first two terms, 1/2 mass 1 theta dot squared L squared. From the second term, 1/2 mr theta dot squared L squared over 4. And then from the third term, 1/2, this would be mass of the rod, and then we'll have the theta dot squared, and then the L cubed over 12. So we could actually combine that into a 1/2, and then we have essentially an effective mass, m1 plus mr over 4 plus mr over 12 times L squared. And that's going to be the total kinetic energy. And notice that if, there's a theta dot squared here. Notice that if the mass of the rod is 0, then this is the same formula that we got before.